morning. We begin with a quick review of lecture number 23 and then the new concepts that we want to introduce in today's lecture. The substantial focus is going to be on a very powerful model that we have, which is the model which we refer to as the wide-sense stationary uncorrelated scattering model. And it is one of the things that helps us completely characterize a wireless channel. Time domain, frequency domain, Doppler, all of the elements are captured in this model, so it's a very important model. We will definitely spend time on that. We have already looked at the concept of coherence time when we talked about the example in Say and Vishwanath, and we will now formalize it using the wide-sense stationary WSSUS model. And of course, there will be lots of simple examples to help us capture the concepts even as we go along. So let's begin with a quick summary of the points that we have discussed in the last class, and then we will move on to the new points in today's class. So in the last class, we have looked at the Nakagami M fading. So let me write down that our interest is to study Rayleigh fading. Rayleigh is the case of interest, of lot of interest. But several times the environment requires us to characterize other channels as well. So we come up with the Ricean when there is a line of sight component. Depending upon the amount of line of sight component relative to the non-line of sight, you get a family of distributions. Then we also have the Nakagami M distribution, which is obtained from the experimental data. Maybe it's okay to sort of say that these two are in some way equivalent because they are covering the same, except that Nakagami M is a broader class of distributions. So the Ricean distribution will be characterized by means of the Rice factor K. Rice factor K, the Nakagami M will be through the fading figure. M is equal to fading figure, and they are related by the relationship we have given in the last class, but let me just write it down. K plus 1 whole squared divided by 2k plus 1. That says that I can relate K to M and M to K. That sort of makes me able to go from Ricean to Nakagami. Now, interestingly, both of these have the Rayleigh as a special case. So in the case of Ricean, it will be K equal to 0. In the case of Nakagami, it's M equal to 1. They give you that as a special case, and it's useful for us to keep that relationship in mind, because when we get expressions for the bit error rate using Nakagami M, you can get the Rayleigh as a special case by substituting the specific value of the fading figure. So in the context of the bit error rate calculations, we introduced the notion of the moment generating function. Moment generating function we can talk about for any distribution, but we are primarily interested in the distribution of SNR. We are also interested in the distribution of the envelope, but SNR is very useful for us. F gamma of gamma, if this is the PDF of the instantaneous SNR. Instantaneous SNR, we would be very interested to understand what would be the phi gamma of S, which will be minus infinity to infinity the distribution e power s gamma d gamma. Again, we derived it for the Rayleigh fading channel, for the Rayleigh fading, and said that the moment generating functions are for the Ricean and Nakagami are given in Andrea Goldsmith, so Goldsmith's book. So therefore, this is just as an illustrative example. For the Rayleigh fading channel, the instantaneous SNR has an exponential distribution, and the moment generating function is given by 1 minus gamma s. Okay, now we also showed how we can calculate the bit error rate of dBPSK. dBPSK through direct integration, also through the use of the moment generating function. Let me just capture that again, the interpretation in terms of a Laplace transform. Laplace transform and also in terms of the expected value. Both of them are useful for us. Keep in mind that we have defined a region of convergence, and we just want to keep that a picture in mind as well. Okay, so now the moment generating function, how did we use it to calculate the bit error rate of dBPSK? We said the integral of interest is half e power minus gamma f gamma of gamma. That's the expression for the bit error rate. When you integrate it over the range of gamma, that gives you the bit error rate in the fading channel. Then we wrote down the expression for the phi gamma of S, that's the moment generating function, and saw the similarities between these two, and then said, well, this is nothing but a special case of the moment generating function evaluated at a specific value S equal to -1, which lies in the region of convergence. And of course, the scale factor half just comes into the picture. Now, I would like to extend this usefulness. You may think, well, it's only for dBPSK, what about others? So there is a very broad class of modulations where the probability of error in AWGN, if it is of the form C1 e power minus C2 gamma. C1 is a constant, C2 is a constant, and basically it characterizes a bit error rate, depends on the modulation type that we have. Now, if we have a modulation of this type, then the probability of error in the fading channel will be integral 0 through infinity C1 e power minus C2 gamma f gamma of gamma d gamma. That's the general expression for the probability of error given the distribution of the SNR. Now, notice that this can also be readily linked to the moment generating function. C1 is a constant that comes out of the expression. This is phi gamma of S, where S is evaluated at minus C2. Again, it's for a broad class of transfer function. As long as the error is of the form something e power minus C2 gamma, you can quickly derive that expression. So very quickly, if I were to ask you to evaluate this expression in Rayleigh fading, I wouldn't even look at the integral. I would straight away say that the phi gamma of S in the Rayleigh fading is 1 over 1 minus gamma S. So the bit error rate in Rayleigh fading is going to be C1, what is that? Divided by 1 plus C2 gamma. That's it. That's the expression for, because basically I took phi gamma of S, kept the constant, and then substituted S is equal to minus C2. High SNR approximation would be, given that I have my probability of error expression as C1 by 1 plus C2 gamma, what's the highest SNR approximation? You should be able to get this. Well, it basically says that gamma is very large, so C2 gamma is going to dominate over 1. So it will be asymptotically, this will be C1 by C2 gamma. That's it. The highest SNR approximation always says that gamma is large. So if there are other constants, it will dominate over the other constants, and therefore easy for, becomes a useful way of approximating. Okay, I would like to now go back and address one more question. Now, okay, what about if the error function is not exponential? What if it's a Q function and I have some arbitrary PDF? And again, to anticipate that question, let's look at a example. Again, it's very straightforward. So, for example, GMSK, yesterday we said that the BER in AWGN was approximated by Q of square root of 1.4 gamma. Okay, now what do? Do I go back and redo the integration? No, we showed that you can just substitute and get that. So in the general case, if my error function is of the form q of root beta gamma, beta is some constant, and many of our modulation schemes will fall into this picture. The constant changes, but ultimately it will be of the form beta gamma. So this we can then, through the process of substitution, whatever we have done, I believe we showed it in the last class, or if not, through the process of substitution, where you would do gamma replaced by beta gamma by 2 in the expressions that we have, that will give us 1 minus square root of beta gamma divided by 2 plus beta gamma. And the highest NR approximation in this case, in the case of BPSK, was 1 over 4 gamma. If you replace it with this expression, it becomes 1 over 2 beta gamma at highest NR. Okay, so whether it is the exponential form or the complementary error function form, there are certain simple tricks that you can use to get the bit rate expression. But of course, there is a lot more to the BER analysis than just getting the basic form, and that is where I would like to highlight some of the applications of what we are going to be discussing today. So any questions on what we have covered in lecture 23? Basically a new type of fading which has a broader characterization, really as a special case of the Nakagami M with a fading figure where M equal to 1. Then the moment generating function and its role in computing the bit error rate, and also some simple techniques for getting the expressions when you have a form q is equal to root beta gamma, or when you have the form that we discussed just now where you have the probability of error is C1 e power minus C2 gamma. So these are two very broad categories of expressions for the different modulation schemes that we will encounter, and therefore we have some simple tools to calculate the basic bit error rate. But as I mentioned, this course is not about the basic. The basic is what you have done in digital communications. We've just showed you that, okay, you can extend it to the fading channel. But this course is all about taking that BER performance in fading and making it go closer to AWG. That's where the trick is, and that's where the challenge lies. Okay, so that's where we pick up today's lecture. So as a first motivation for the types of things we're going to be studying, let me write down an example or an application. Again, it's a simple example, but again it gives you a lot of insight and into the motivation for the things that we are going to be doing. So consider that I have a base station and I have a mobile which has got two antennas. Okay, two antennas. And the transmission from the base station is picked up by both antennas, but because of their spacing between the antennas, the channels are different, and this one is seeing an instantaneous SNR gamma 1, instantaneous gamma 2. Now at the receiver, I can do one of two things. I can do what is called antenna selection. Antenna selection would be a very simple method which says compare gamma 1 and gamma 2. If gamma 2 is higher, pick gamma 2. If gamma 1 is higher, pick gamma 2. So that is what we call as antenna selection. So you compare gamma 1 is greater than or less than gamma 2, and then you pick the stronger antenna. That is one way of doing it. And this would also shift the change your statistics. So there is a selection diversity. Now there is an even better form of diversity, which I will for now call it optimal diversity. Optimal diversity, which says you don't need to pick the larger of the two, you can actually do a form of combining so that your resultant diversity. So in this case, the gamma diversity is equal to the max of gamma 1 comma gamma 2, correct? That's selection diversity. Optimum diversity says you can actually achieve gamma 1 plus gamma 2. This is very, very powerful because even if both antennas are in a fade, you may actually be able to combine them and detect the signal because the combination of the two SNRs may be above the threshold that you can detect. So this is very, very useful for us. Now, Notice that gamma 1 and gamma 2 are the instantaneous SNRs, both of which are random variables, both of which will have their own distribution, and there is no way we can make the assumption that they are identically distributed, because one antenna may be in the top of the phone, one antenna may be inside, one antenna may be behind the battery. So we cannot make the assumption that both of them are identically distributed. Now that's exactly where the challenge comes. So if I have a new random variable which is gamma 1 plus gamma 2, where I do not have the guarantee that they are identically distributed, then I have a problem, because I know if you tell me, give me the PDF of gamma diversity, I have a problem, because most of the familiar methods that we have worked with says assume that the variables that you are adding are identically distributed. So here is the challenge that is before us. So we want to estimate the probability of error under maximal ratio combining or optimal diversity. Okay, optimal diversity. So this is going to be integral 0 to infinity, probability of error under gamma diversity, and I will ask you to give me the PDF of gamma diversity. Okay, so this is going to be an absolutely essential requirement for me to characterize the behavior under these types of scenarios. And so the question is, what is gamma diversity, what is this equal to? Okay, and I'm sure you are familiar with in probability statistics we often do this type of a problem. I is equal to 1 to n xi, and we find out that this is equal to y, and find out, but we often make the assumption that they are identically distributed. So that sort of makes but it is definitely doable if you have a different distribution, but not straightforward. So this is where moment generating functions come and play an important role. So let me just define the method, and then we will do. So let xi I is equal to 1 through n be a set of independent random variables. That's all the assumption that we are making. Be a set of independent random variables, not identically distributed. Okay, so y is equal to summation I equal to 1 to n xi. The moment generating function of y is given by expected value of e power sy, correct? That's the expected interpretation as an expected value, the moment generating function. So this is the moment generating function that we are interested in. So now substitute for y, this becomes expected value of e power s times summation over I xi. Basically you have replaced y with summation of xi. Basically expand the summation and rewrite the expressions. This becomes expected value, you are adding the power, so therefore it's like multiplying the exponents, multiplying the exponentials. So product of I is equal to 1 through n expected value of s times xi. Okay, I've just rewritten it, just a simple rewriting of this expression. Okay, so the right hand side is a expectation of n random variables, of a function of n random variables. So I would now get a integral situation where there are n integrals, each of which going from minus infinity to infinity, whatever is the range of the, this is the general definitions. So from minus infinity to infinity, there will be n such integrals. Product of I is equal to 1 through n e power s xi. I must have the joint PDF of these random variables, x1 through xn, then integration over the variables dx1 to dxn. This is what will give me the expected value of the quantity that is within this bracket. Okay, so again I've just rewritten the expressions for the moment generating function of y. Now these are, assumption is that these are independent random variables, so the joint probability is the product of the probabilities, which now says in one step you have the final answer I is equal to 1 through n phi of xi, not gamma I. phi of xi of s. So it's a product of their moment generating, individual moment generating functions, and as long as you know what the distribution of those variables are, you can write down the expression by inspection. There is absolutely no problem for that. Now if it so happens that they are IID, which is very good for us, then it becomes phi x of s raised to the power n. Once again, a very easy thing for us to work with. Now, what is the benefit of all of this? Notice that we said that the moment generating function can be interpreted as a Laplace transform. So, which means that if I have the moment generating function, I can do the inverse Laplace transform and get the PDF. Okay, very straightforward. So, once I get the phi y of s, then I can do the inverse Laplace transform to get the fy of y. So what may have been difficult for me to do directly with the PDFs, it becomes a very easy problem for us when we work with the moment generating function and then do the inverse Laplace transform. Notice that we have used both the mathematical interpretation of MGF as well as the Laplace transform interpretation to our advantage to make sure that we are able to get. In case you're wondering why the name moment generating function, probably you're familiar with this. Phi gamma of s, phi x of s, definition is minus infinity to infinity fx of x e power sx dx. We talked about differentiating an integral. So if you can differentiate for me the moment generating function with respect to s. Differentiate it with respect to s. First term will be with respect to the upper limit, second term with respect to lower limit, both are constants are not in the picture. Then you have to differentiate the integrand. So basically differentiate the integrand and set s equal to 0. If you do the differentiation, should be straightforward. What you should get inside the bracket is e power minus integral minus infinity to infinity x times fx of x dx, which is nothing but expected value of x. And once you have the moment generating function, it's very straightforward. You take the second derivative, d squared phi psi x of s divided ds squared, set s equal to 0. You will get expected value of x squared. And if you want the higher order moments, it's just more additional differentiation. So moment generating functions have a very useful role in the context of mathematics. You may not have seen it, but for us it's very, very useful, because but for the moment generating function, some of these PDFs would be quite difficult for us to work with. Okay, any questions? So moment generating functions, I will assume that you are familiar with it, that you can apply the moment generating function to get the more difficult PDFs and then use that to get the bit error rates of the modulation schemes that we will encounter. Okay, that's something that is a useful tool for you to have once you, as we study this course. Okay, now that has set the stage for us to talk about the important model that we are going to be working with, Whiteson stationary uncorrelated scattering model for a fading channel. So for this, I would like us to revisit the multipath model that we had derived earlier when we first talked about Rayleigh fading. Okay, so go back, turn your pages in your notes. I don't have the lecture number, but I'm sure you'll see that this is just before we derived the multipath model. So we said that each of these multipath components, the large number of multipath components which are going to get superposed, each of them has got an angle of arrival based on their the direction of the multipath component. That means their Dopplers are different. So based on that, we said that there is a channel gain alpha n and there is a phase term phi n t comma tau, okay, e power j. Wait a minute, I should write that. So alpha n t comma tau e power j phi of t comma tau. Okay, so I want to focus in on the part phi of t comma tau. there should be an n here. Okay. So phi n t comma tau. Again, please, if you can refresh, just turn your pages back to that, but if not, I will just write the expression. Minus 2 pi fc tau n of t minus 2 pi fdn t minus tau n of t. Okay, this was the expression for the resultant phase of that particular component, and we actually gave them some names. This one we called as theta n t comma tau, and the next one we labeled it as psi n t comma tau. Okay, again, exactly copied from the previous page. So what this model told us was that the received signal R of t can be written as a superposition of many components, where this is resultant of alpha n of t, that's the time varying gain, and e power j phi n t comma tau times u of t minus tau n of t. So basically you will get shifted versions of the transmitted signal. Transmitted signal is u of t, and they are going to be scaled by these complex numbers and then added together to produce the resultant signal. So we said that the channel response, not impulse response, channel response, because it's not an LTI system, so I cannot call it an impulse response. Channel response at a given time can be characterized as a two-dimensional variable h of t comma tau. This is given by summation over n alpha n of t e power j phi n of t comma tau and delta of tau minus tau n of t. Okay. This was the channel response, and again, if you recall, we explained this or used a three-dimensional representation. So if you think of this as the amplitude, this as the delay dimension, which is indicated by tau, this is the time dimension, which is indicated by t. So at a given time instant, a snapshot, I may get some number of multipath components. So we said that, okay, I could get a multipath component like this, some distribution. Then at another time instant which is a different snapshot, I may get a channel which is very different. So for example, the first path may be 1, the second path may have gone off, and then you have a second cup. So basically this is what it looks like when you look at a channel response at different instances of time, and these are the multipath characterization that we have obtained. Okay, I hope you are familiar with it. You are able to recall whatever we have discussed in the last class when we talked about the multipath model. So start with using that as my starting point. I want to build the WSSUS model, and therefore that's why we are rewriting this equation. So I would now like you to focus on the phase of the multipath component. So that is phi n of t comma tau. That's the phase response. Okay. Now the previous characterization was okay for the earlier discussion, but the same thing I want to write it in a slightly different manner for the particular analysis that we are going to be doing now. So I'm going to rewrite it in the following form. Again, you can verify that's exactly the same. 2 pi fc minus fd comma n minus 2 pi fdn times t. And I would like to label this as theta n hat. The reason I'm using theta n hat is because theta n, I've used it for something else. Okay, now going through, am I missing something? Oh, tau. Thank you. I missed a tau n of t. That's multiply. It's not exponent. It's multiplying that bracket term in the bracket. Okay. Using the same arguments as before, because these Doppler shifts can be based on the angle of arrival. This term theta n can lie anywhere between minus pi to pi. There is no preferred direction. So therefore, we can say that, if there are large number of these multipath components, then this theta n hat is basically, there is no preferred direction. It is uniform in minus pi to pi. Minus pi to pi, I have no preferred direction. So in other words, if this now captures our understanding based on the angle of arrival, this theta n hats are uniform in the azimuth plane. That's the horizontal xy direction in the azimuthal plane. Okay, so that's a observation that again based on the earlier reasoning, same reasoning applied again in the azimuthal plane. Okay, it has a very useful and a very important thing that is going to come about. So the first thing that we ask is, what is the expected value of theta n? Expected value of theta n? 0. Uniform in this distribution, so there is no, it can be minus plus. If you take it as minus pi to pi, the expected value is 0. Now think and answer this question. Expected value of e power j theta n hat. What is that? Write the next step and then you may change your mind. Cos theta n hat plus j times sin theta n hat. Is that correct? And uniform distribution. So what is that? It's equal to 0. Okay. So actually 0 is the correct answer. Of course you can write down the expected value, but basically you are integrating sine or cosine over an entire period, so therefore it will go to 0. So this is a very useful result for us to keep in mind and extend. Now let me extend this to the following. So what is expected value of e power j theta n hat minus theta m hat, where n is not equal to m? If n is not equal to m, and if theta n and theta m are independent, right? There is no, that means you are basically looking at two multipath components. There is no relationship between their angles of arrival, they are independent of each other. So then this also becomes delta of n minus m. It's equal to 1 if it is if e power j theta n is there. Otherwise it will basically it is non-zero only when it is only when it's equal in this fashion. Okay, so that tells me that I can now write the following expression. I want, what am I trying to do? Maybe even before we do that, see this red channel response. Now I want to know how this red channel response changes as a function of time. So I'm not worried about the delay dimension. I'm worried about how this is going to change at different instances of time, as along these dots. That's my intent for the task that I'm doing. So the thing that I'm going to do now is calculate expected value of h of t comma tau, h star of t plus delta t. Just a small delta increase in the time, but I'm not changing the tau dimension. I'm not worried about the tau dimension right now. I can even assume that there is no dispersion. There's only one single tap. Is that, if that's helpful, you can take it up in that fashion. This is an important expression. So what are we trying to do? I'm trying to get the autocorrelation of the channel response. So basically I'm trying to see between time t and t plus delta t, is there any correlation between the, so this is a autocorrelation expression for the autocorrelation of the channel impulse response at a given tau. Notice that tau is the same for both. I'm just changing time dimension. So I'm going along the time dimension at a given tau and trying to see if there is time correlation. So this is basically, we will write down the expression. May look a little messy when you write down, but actually keep in mind I'm trying to get an understanding of how this channel changes. Is it totally uncorrelated from time to time? That is, channel at this time instant or how does it change? So that's what we are trying to get. So this is written as expected value of, write down the expression for h of t comma tau. Okay, that's the first summation. Let's call it as summation over n. Then h conjugate, that will also give you another summation. We'll have to keep different variables of summation, independent variables. So we will call it n and m. So the expression inside will be alpha n of t, alpha m of t plus delta t. That's part from the second summation. Alpha is a real valued parameter because it's the amplitude, so therefore there's no conjugation there. All the phase terms will see a conjugation. E power j theta n hat minus theta m hat. If I miss something, please catch it. Let me know. E power minus j 2 pi fd comma n minus fd comma m times t. I've run out of space, but let me just write the last term. E power j 2 pi fd m delta t. Okay, so I hope I've got all of the terms with the correct signs, and this is within the bracket. So basically this is the expectation that we are interested in looking at. Okay. Now of course the alphas are completely independent of the angles of arrival. So basically we will quickly try to segregate and try to get the things of interest. So this is a parameter of interest for us. So expected value of alpha n, alpha m is an important parameter. So let's quickly analyze that. So if you expand this expression, notice that you will get a expected value of e power j theta n minus theta m hat. So that is equal to delta of n minus m. So which means the double summation will collapse to a single summation. We'll work with a single summation. Summation over n, I'm going to take the expected value inside. It will now be alpha n of t, alpha n of t plus tau, alpha n t plus delta t. So that is one of the terms. Then notice that wherever there is n and m are the same, so some of the terms have cancelled out, and what we are left with is another term which is expected value of e power j 2 pi f d n delta t. Okay. This term gave us the delta function. So which means this term goes away, leaving you only two terms in the expectation. One of them is the amplitudes, the other one is the connected to the phase. Okay. So there are two things that we will try to capture and very quickly get the key results that we have. So if you make the assumption that delta t is small, so this can be written as e power alpha n t whole magnitude squared. So in some sense this is like the power of the received signal. So this has the notion of the power. Okay, some measure of power, amplitude squared is coming into the picture, expected value of that. But the second term maybe not so obvious. Let's take a closer look. So the second term is what we are going to focus on, expected value of e power j 2 pi f d n times delta t. Actually, the answer comes in just one step. So the insight comes from this particular observation. Fdn is maximum Doppler times cosine of the angle between the direction of propagation and the direction of motion. So, and because there are large number of scatterers, from our model we have always been saying that beta is uniformly distributed. Uniformly distributed. The only thing that is random here is fd. So therefore I know that that depends on beta, and beta is uniformly distributed, so I can calculate this expected value. Okay, so that is the, expected value here will be minus pi to pi. It's uniformly distributed, so it's 1 over 2 pi e power j 2 pi. It's now f uppercase D because it's we're writing it as maximum Doppler, where f uppercase D is max Doppler, maximum Doppler shift or maximum Doppler frequency, fd times delta t times cosine beta d beta. Okay, that's the random variable there. We've got the PDF and we have written down this expression. Okay. Now, this is also of the form of a another known function, zeroth order Bessel function. Let me just write down the definition. J0 of x is 1 over pi integral 0 to pi e power j x cos beta d beta. Okay. So, notice that it's of the form. So, this is this particular one is going from not from 0 to pi but from minus pi to pi. Split it as two parts. You can show that each of them is equal to 1/2 of a Bessel function and 1/2 of the same Bessel argument. The argument that is of this is the expression that is here, which is 2 pi fd times delta t. 2 pi fd delta t. Okay. Now, if you take a minute to sort of write it down systematically, I'm sure there is nothing complicated here, but you may be wondering, why am I doing this? Because what at the end of the day, what it is. So, basically, this tells us that the autocorrelation is equal to expected value summation expected value of alpha squared, alpha n squared, where the n is over all the. So, if I call this as some measure of power, let me call it as P naught. It's some average value, that's some P naught. So, my autocorrelation is equal to P naught, which is a constant, times J naught 2 pi fd times delta t. Okay. The most important thing is the autocorrelation is of the form of a Bessel function. That's interesting enough, but look at the argument of the Bessel function. It does not depend on t, it depends only on delta t. Okay. So, this is what makes it a WSS process. The amplitude the channel response as it varies as a function of time looks like a stationary, Whiteson stationary random process. Okay. So, therefore, there is correlation between any two adjacent points. It does not depend on t, it depends on the time separation between those 2 points, and that is consistent wherever you observe. It's a very useful parameter for us to characterize. So, let me write it down. So, this is the Whiteson stationary property, WSS property in the t dimension, in the time dimension. In other words, for a given tau, if I observe the time variation or the autocorrelation of the channel response, RH is actually a function of delta t comma tau, the autocorrelation function, and this is equal to a constant P0 times J0 2 pi fd times delta t. That's the first part of the WSSUS model, and this is going to give us a lot of very useful insights. In a few minutes, we'll quickly capture that. So, I hope you'll be able to go through the derivation, look at the definition of the zeroth order Bessel function. Maybe we just write this down. J0 is a zeroth order Bessel function of the first kind. Again, that's a standard function, not defining something different. Bessel function of the first kind. And it has got certain properties which we would like to understand and to exploit. The first of it is going to come immediately. So let's quickly look at the behavior of this J0 function. The J0 function, if you plot or if you look at it, looks like a like a sinc function. Okay, looks like a sinc function. Okay, so it basically starts off at a high value, then cuts at 0. Now notice that your argument, so this is your time spacing, which means this is a function of delta t. This is your RH of delta t, comma tau. Tau is not in the picture, you are only plotting the variation as a function of delta t. Now if my Doppler increases, that means if I have, so notice that so the point at which this one crosses, the Bessel function crosses, is when the argument of the Bessel function is 2.4. In other words, J0 of 2.4 is equal to 0. Okay, that's from the plot of the Bessel function. So which says that basically the 0 crossing will occur when 2 pi fd delta t is equal to 2.4. So I have drawn this for some fd. Okay, this red is corresponds to some fd. Now if I have another Doppler which is fd dash, which is greater than fd. Okay, notice that fd is larger, so delta t where the 0 crossing occurs will occur earlier. So the green line is going to look like this. So this is for a higher Doppler. So this is fd dash, and by the same token, if I have a fd double dash which is less than fd, the graph is going to be like this, that is fd double dash. So in general, this is the direction of decreasing fd. So as I decrease fd, it will become shallower and shallower. As you increase fd, it will become steeper and steeper. Okay, so the basic observation is that I get the intuition about these graphs by saying, given this equation, if fd decreases, that means delta t will increase, and basically vice versa. You can then interpret this case. But insight is most important for our discussions. So let's take the following special case. There's a special case. Special case is fd equal to 0. So what happens? The channel is not changing at all, no Doppler, right? Basically fd equal to 0 means there's no mobility, no change. So channel is not changing. How should it reflect in my autocorrelation? It should look like a straight line, which is what it is. J0 of 0 is equal to 1, and it's equal to constant all the way along. So basically you can draw another line which says this corresponds to fd equal to 0. Okay, that's again very consistent with what we would expect. Okay, now the observations that we are making is that low Doppler, the channel is highly correlated. Basically, you have to, the delta t for which the channel remains correlated is much higher. So when you look at pedestrian scenarios, pedestrian is low Doppler, and this gives us a very good structured framework to make statements. Remember previously when we said low Doppler means your fade will last a long time. Now you can tell exactly how long the fade is going to last based on the Doppler, because I now know how long it's, because the channel is going to change very slowly. If I am a pedestrian user and I go into a situation where there is a fade, I'm going to be stuck in the fade for quite some time, except if I use frequency hopping or some other method, I'm going to be in trouble. So this actually now starts to give us a very solid way of characterizing the the system and ability to work with that. Okay, so what I would like you to do is read up the corresponding portions either from Molish or from Goldsmith. Both of these are equally good because this is now the framework on which we have addressed the first aspect, Whiteson stationary part of it. Now what happens to the uncorrelated scattering, and what happens to the interactions between the time and frequency domain, and what are the implications in terms of the system design. Now those are the key things that we would like to develop and like to build up and understand, that we now can make very careful and correct statements about saying what should be the size of the interleaver when there is low Doppler. How do I design that? This is going to tell me how long I'm going to stay correlated in a fading channel, and therefore my interleaver must be accordingly designed. My coding system must be designed. If I do antenna diversity, I know how to do that. So basically all of the pieces now have to come together. So the whole discussion about Whiteson stationary uncorrelated scattering, think of it as a jigsaw puzzle. Each day you're going to get a few pieces. You've got to put them all together, and then finally you see the grand painting and you say, oh, okay, everything sort of falls into place. So we have done a few pieces. You need to fill in the rest in the next lectures. Thank you.